Alrighty, howdy everyone. We'll get started. Hi, welcome. How are we doing today? Good, great. Everyone survived our first exam. Yeah, ish. So if you're in Dr. Bengali's class, you should already have your grades visible to you. I highly recommend looking at Gradescope. There were just a couple issues scanning the Scantrons in. So sometimes they were a little wonky, so just make sure that your test matches what it's supposed to. And then if you're in Dr. Altamos's, that should come out probably Friday. I think there was the last little bit of makeups that happened today, and then I'm done grading. I just need to grade the two that I took them today, and then you're done. With that, I think that's all the announcements I have. Any questions for me? Cool. What do you want to see today? Quantum numbers? Yeah. Okay, that's what I was figuring we were gonna do.
We went over today and most as well.
Okay, so we're gonna start with quantum numbers. So can someone tell me what a quantum number is? Yes, yep. So it determines like where an electron is. And I want you to think of quantum numbers as like your UIN, but for an electron, right? This identifies a specific electron. Identity of an electron. Okay. How many numbers are in a quantum number? There's 4. What's our first one? What's the letter for it? N. Yep. What does N tell us? Yes. The energy level is what I'm looking for. Okay. Talking about the energy level. Does the number correlate with how much energy you have? Right, is that a direct relationship? Right, if you have an energy level 1, N equals 1, or an energy level N equals 7, which one has more energy? the 7, right? So the higher you get in your n equals whatever number, the more energy that electron is gonna have. Does that mean it's closer or farther away from the nucleus? It's farther away. So those higher electron or the higher n values means that electron is farther and farther away from the center of that atom. What are our constraints for the numbers that n can be? It can be 1. Can it be 0? No, right? It has to be 1, 2, 3, and so on. Can it be 1.5? Nope, it has to be a whole number. What's the next quantum number? This is L. What does L tell us? This tells us our orbital. This tells us our subshell. I guess this is more of the shape of the orbital. What does L have to be? L has to be n minus 1. Or it can be L minus 1. N minus 1, excuse me. So if L equals 2, if n equals 2, what can L equal? 1 or 0, right? If n equals 4, what can L be? 0, 1, 2, 3. Yep. All of those options will exist for an L is equal to 4. Right? You will always have, if n is equal to 4, you will always have something 4, and then 0. You'll always have something that's 4, 1. You'll always have something that's 4, 2, always something that's 4, 3, right? All of those combinations will exist. Any questions on L? So if L equals 0, what shape do we have? This is going to be a sphere, and what do we call that? What letter do we give that sphere? This is an s orbital. Okay. If L equals 1, what is this one? This is the p orbital. If L equals 2, d. And if L equals 3, good. Okay, you really only need to know about 0, 1, 2, and 3. Really 0, 1, 2 are what we're really going to test you on. But you will see some problems with a 3 for L, when L is equal to 3. Anything past the F orbital, you just start using the alphabet. So F, G, H, I, right? If you have some weird question that you come across of. But you really only need F. Questions? Yeah. Yes, yep. But we don't need to know those. Yeah. What's the next quantum number? This is m sub L. What does this tell us? This is our orientation. Okay, so this is where it is around the nucleus. What are our constraints for L, for m sub L, what it can be? Yes, but where does that rule come from? Yep, so it can be plus or minus L. So I always think of this as minus L, 0, plus L. Right, if you think of a number line, it can go between the negative and positive. You have to go through 0 for L. Yep, yep. So if L is equal to 1, M sub L equals what? -1, 0, 1. It does not matter what order you put this in. You can go 0, 1, -1. Call you a psychopath if you do it that way. But you could do 1, 0, -1, any other combination of that you want. I always think of this as a number line, so I always go negative on my left, positive on my right. If L is equal to 3, what is M sub L? Yep. Right. I think that one's the easiest to see the number line, right? We have to go through all of the numbers from -3 to +3. So how many orbitals are in the M sub are in the L is equal to 3? Right, when M sub L, there's 7 total orbitals, yes. When L is equal to 3.
When you say 7 total orbitals, that means like 7 of the individual shapes.
Yeah, so like within the M sub, so when L is equal to 3, M sub L could equal any of those 3 numbers. Those 3 numbers correlate to a different shape in each one of them, or a different orientation. So for M sub, or for when L is equal to 1 and M sub L can equal -1, 0, or 1, that's the dumbbells. That one's the easiest for me to kind of see, because you can either have it going along the y-axis, the x-axis, or the z-axis. Yep, so that's why there's 3 of them, because there's 3 different orientations that one can be. For the L is equal to 3, we now have 7 different orientations that this one can be. And that just gets really funky with math that we don't need to know for this class.
Does that mean like there are like 7 orientations?
Yes, yep. And like when L is equal to 2, this M sub L is equal to -2, -1, 0, 1, and 2. So you have the one that's, right, it has the clover that would just be along the x-axis. You could do that same clover y-axis, same clover z-axis. And then you have, it's like, I think it's x squared or something. That's a little bit funkier. And then you have that donut that's like the top and bottom with the donut in the center. Right, and that just is because you're squaring things in the algebra, whatever. But it's all different orientations that one can be. And so each one of those numbers correlates to a different orientation. Yep. Does that make sense? Okay. You don't need to worry why the orientation is the way it is. Just know that it is a different orientation depending on the M sub L number. Alrighty. And then the last quantum number we have is what? This is M sub S. What does this tell us? Up or down, what does that correlate to? The electron spin, yep. What are our 2 values for M sub S? It can be +1/2 or -1/2. Or you could either have an upward spin, which is the +1/2, or a downward spin, which is the -1/2. By convention, if there's just 1 electron, usually you get the +1/2 first and then the -1/2 second. So you usually do an upward spin electron first before a downward spin electron. Alrighty, questions here? Yep. That I don't know. I don't know if it has to do with like spins canceling, and so they would rather say plus and minus 1/2, so then the spins cancel, so that because it's 0. Or if it's some other electron thing that I don't know because I don't do electron chemistry. You don't unless you're like given a picture. So in class on Tuesday, we didn't start getting 2 pictures yet, but you talk about that tomorrow. But essentially, right, you're gonna draw a diagram, and this first one right here, this one's an upward facing arrow, which means that it is the upward spin. So this one gets the +1/2. The downward is the downward spin, so that gets the -1/2. Yep. And then again, by convention, you usually give it a +1/2 first. Okay, any questions here? Alrighty, so again, this identifies an electron, right? This says, okay, if you go to this specific spot right here, this is the electron that I'm talking about. So if we had a quantum number and it was 200 +1/2. What could you tell me about this electron? What energy level is it in? Mhm. What subshell is it in? It is in the S subshell. So what's the shape of this? It's a sphere. This orientation doesn't really matter. Right, it's a sphere, it's around the nucleus. And then what kind of spin does it have? Yep.
The ones that are in sphere, do they have to have like 0 for the orientation?
Yes, yep. So one thing about quantum numbers is that if you see a 0 for your L, you will always be followed by a 0 for your Epsilon L. There's no other option that it can be. So you'll always say 0, 0 next to each other. Right, you could have one that was 2, 1, 0 +1/2, right? In this case, the 0 is still there, but that M sub L is equal to 1, or the L is equal to 1 now. So now our options are -1, 0, and +1 for M sub L. But if you see a 0 come first with your L, then it will always be followed by another 0. Okay, let's practice a little bit. Okay, so this one we have, which of the following are proper quantum numbers? We have 6 different options. I'll give you a couple minutes. Just look at this, say if it's yes or no.
So because, M contributes like energy level and like it kind of like runs on a ladder farther and farther away, does that mean these shapes technically have like infinite theoretical quantity? They could expand as far as
So like for that specific energy level, it would be quantized to that size. Then if you had a higher, right, if you excite that electron to a higher energy level, then it jumps to that larger size that's farther away from the nucleus.
So the sphere wouldn't like expand, so like you jump to a different.
Right, yes, and that's where, right, we talked about the nodes. So it was like this guy, right? So, oops. So the sphere is expanding because it has to get farther away from the nucleus. So that sphere is technically bigger because it has to cover a larger space.
Okay.
But right at that point at the bottom of the graph, there would be no sphere there.
Okay, only at the.
Yes, yep, like because and you would never find an electron at that sphere, and that's where like the light and dark.
So it's not like they're in the whole volume of the sphere, just like.
Yes, yep, yep. And it's not the volume of this sphere because we know that energy levels are quantized. So it can only be at that certain energy length away from the nucleus. Yes, yep. So it can't be going in and out closer to the nucleus that way. It has to be standing around where that is.
Like, as long as the energy level rises the surface of the sphere, you get further.
Yes, yep, yep. Right, so that's why you can have an energy level that's 1, that's an S subshell, but you can also have an energy level that's 7, that also has an S. It's just gonna be that shape farther away. Alrighty, do we come up with answers for this question here? What about A? Is that a proper quantum number?
Yeah.
Yep. What subshell is this in? This is in the S subshell, good. What about B? What's wrong with this one? Yep, so L, this one here cannot be 1, this one has to be 0. That would make it a proper quantum number. Does anyone know how many electrons can be in a specific orbital? 2, right? So if we look at B and A, now that we've corrected those quantum numbers, those would be the 2 first electrons. So that would be the 2 electrons that are in helium, right? Would have those 2 quantum numbers.
They can still spin differently.
Yep, because you will always pair them to have different spins. If 2 electrons are in the same orbital, they must have different spins. Yep. So that's why those are the 2 that work together, because there's a +1/2 in B and a -1/2 in A. Okay, what about C? Is that a good one? Yep, what orbital is this one in? This is the F orbital. This is going to be the 4F orbital, we'll call it, right? Because it's in the 4th energy level, and then the F orbital. This would be 1s. This one would also be 1s once we fixed it. Yep, if it was correct, it would be 1s. What about D? Improper. What one word do we have to change there? Yep, this one. This one cannot be 2. This one has to be either 0 or 1. If it was 0, what subshell would it be in? Yep, so we can have 2s, or if it was 1, what would it be? 2p. Perfect. What about E? That one's good. What subshell are we in here? D, and what's the energy level? Good. So this is the 3D orbital. And what about F? That one's also good. This one would be the 6F orbital. Are we understanding how we're reading these quantum numbers? Yep. Okay. Does this help make sense? Kind of just like a puzzle. Right there, remember they're always pointing towards an electron. So all of these would correlate to an electron that's on the periodic table. And you could find, okay, I need to go to this specific one here, and you can find it from there. Yep, you're in the 3D subshell. Yep. Alrighty. Just a couple more things about quantum numbers and just like subshells and orbital in general. If we have an S subshell, how many orbitals do we have? How many options for N sub L do we have? Just one, right? What's their option for M sub L if S is the subshell? 0, right? So you have one option for M sub L. How many orbitals do we have? Just one. How many electrons can we have in the S subshell? Well, you'll talk about this tomorrow, but in one specific orbital, there can only ever be 2 electrons maximum. You can have 1, you can have 0, but you can have a maximum of 2. Ish, like yes and no. You'll see where the 8 valence electrons comes from because of the orbitals. When we have the p subshell, how many orbitals do we have? We have 3, right? What options do we have for p? We can have -1, 0, or 1. So this is 3. But that's when L is equal to 1. What about when L is equal to 0? Yep, and then we just have one option. So then how many orbitals do we have there? 1. So we have a total of 4 orbitals in the p subshell. So how many total electrons can we have in the p subshell? We can have 8, right? Because we have 4 orbitals, they each get 2 electrons. So that's going to be 8 total electrons. Do we see where the 4 came from? When we have the D subshell, what are our options for L? So for M sub L, we can have 0, we can have -1, 0, or 1. We can have -2, -1, 0, 1, and 2. So how many total orbitals are in the D subshell? Mm-hmm. 9 orbitals, 18 electrons. Right, because we count all of our options for M sub L. Questions on how we found that one? Okay, and then the last one we'll talk about is F. What are our options for F? Mm-hmm. All right, we're just building off from the last one. So now the only new thing that we have is this L is equal to 3 option. So how many total electrons do we have? Or sorry, total electrons. How many total orbitals do we have? We have 16. So how many total electrons do we have? 32.
That means like the F orbital is full, you have
Right? And if the f orbital was full, that means you also had to fill all of the d subshell, all of the p subshell, all of the s subshell. So they all compound on each other.
2 plus 8.
Yeah. Yep. For that atom, yes. Yep. But if they're just asking about the f orbital, we say if the f orbital was full, right, then you would have 32. Okay. How do I want? How far did y'all get into osmosis class today?
That's where we're determining energy levels based off like 60 should give us something.
Okay, cool. I was gonna show you that next. I wasn't sure if I was going to totally be off of my rocker or not. Okay. So I love the periodic table. Obviously I'm a chemist. But as a visual tool, I think it is super, super helpful. So when we talked about the S subshell, right, we're talking about the 1s subshell. That's the first energy level. That's the lowest energy level. How many total electrons did we say were in the S subshell? 2. Where do we see 2 on the periodic table? We see helium, right? And then if we have to build up to 2, where's number 1? Hydrogen, right? So the hydrogen and the helium are going to be your first 2 electrons in your quantum numbers. So that's going to correlate to the 1, 0, 0 plus 1/2 and 1, 0, 0 minus 1/2. Okay. Where else do we see 2 on the periodic table? Maybe like a block of 2. Right? If we look right here at our metals, right? How many metals are in this 2 columns right here? We have 2 columns going down. What do you think that's going to correlate to? That's going to be your S subshell. Any electron that's going to be in these elements right here are going to be filling the S subshell. Whether that's the 1, 2, 3, or 4 is going to be filling the S. If we look at these numbers here, 1, 2, 3, 4, what do you think that correlates to? Sorry, the ones going down, like, so it's 1 hydrogen, 2 lithium, 3 sodium. Those are going to be the energy levels, right? So as you go across the periodic table, every time you go down, you're going to be going to your next energy level. So sodium is in the 3s orbital, right? Because it's in the 3rd energy level, and then it's in that first S block that we see. But will be S, that also means the second column will also be S, okay? Any questions on that so far? Do we see that? Okay. How many elements are going across the second energy level, starting at lithium?
8.
8. How many electrons did we say were in the p orbital? We said that was going to be 8. Where did those come from? 2 of them came from what subshell? The S, lithium, beryllium. Where did the other 6 come from? The other 6 come from the right-hand side of the periodic table, the boron, the carbon, the nitrogen, the oxygen, the fluorine, and the neon. Right? Do we see how many elements are there between boron and neon? 6, right? That correlates to the -1, the 0, and the +1 of your p orbitals. And each of them could have 2 electrons, so that's why you get your 6 elements on that right-hand side. So all of those 6, right, this chunk here, that's going to be your P subshell. Anything that's on that portion there will be in the P subshell. Do we all see that a little bit? Are we super lost? Who did I lose? How many did we say were in the d orbital? 18. If we're just talking about the last bit that we added, how many electrons are in there? 10. Do we see a spot of 10? The middle chunk, right? Our transition metals, those are all going to be in our D block, is what we're going to call it. Okay, so when you're filling electrons within titanium, say, you're going to be filling the D block of that titanium metal. If you get all the way to zinc, you fill the D block of zinc. Yep.
So then, like you said, that's aiming for the D block. Like first you for the SP, but then like, we need to do also for D.
Yep. So you can just follow the periodic table across. You can go 1s would be your hydrogen and helium, right? If you wanted to get to titanium, you just have to follow it counting up to titanium. So you would fill 1s, hydrogen to helium. You would fill 2s, lithium and beryllium. You would then fill the 2p, boron, carbon, nitrogen, oxygen, fluorine, nitrogen, or neon, excuse me. We then fill the 3s, the 3p, the 4s, and then so the D block, you're always going to be 1 energy level behind what row it's in. So instead of filling 4D with Scandinavium, you're going to be filling 3D.
Why?
Because it's your energy levels as you get higher up depends on the stability of the atom. And so the 4s is actually lower in energy than the 3D. So you fill the lower energy level first before the higher energy level, right? Because you would want the atom wants to be at rest as much as possible, so the lowest amount of energy possible, right? You would rather be horizontal all day rather than sitting up, so they're going to be horizontal that way. Okay, so you fill the 3D there. Does that make sense? Do we see how we followed that across? Yeah.
So, so you use the other 6 on the right to fill P, but P holds 8.
Yep, because we filled the 2s from the lithium and beryllium, and then that's where 2 come from. The other 6 are from the 2p. So total in the 3rd energy level, we have 8 total, or the 2nd energy level, we have 8 total electrons. 2 come from S, 6 come from P. Yep. Great question. Okay, and then the last one that we talked about was F. How many total are in the F orbital? 32. We said that 2 come from S, 6 come from P, 10 come from D. So how many is left over? What is just like the new section of F that we added? 14. Where is 14 on the periodic table? It's this little island at the bottom, right? Your F block down at the bottom. That's 14 going across. Those all fill your F orbital. Okay, so if you wanted to get there, you have to go through, right? 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, right? 5p, 4d, or 5s, 4d, 5p, 6s, then you jump down to LA. And that's going to be 2 behind whatever row it's in. So that's going to be your 4f orbital. Okay. So this is a useful tool. You will see in your notes that there is a periodic table that shows you like no elements. It just shows you the S block, the P block, the D block, and the F block. And that'll help you that way. And there's been a lot of practice. You'll do electron configurations that'll teach you how to read the periodic table. But it's super useful. So you never have to memorize how many are in each block. Okay, any questions? on that. Hopefully I didn't lose everyone. Alrighty, right, so, right, to kind of summarize, the S will always hold 2. The P will contain 8 total. It'll contain these guys here. And that's going to be 2p, which is 6 electrons. And it'll contain this guy here, which is 2s, which contains 2 electrons, for a total of 8. Yep, yep. Right, later on, when you get into higher energy levels, it might be the 4p or the 4s, right? But we'll just call that for now. The first time you see the p orbital in the second energy level. Okay, for this, L is equal to 2 down here. How many electrons did we say there were? This was 10, right? This is the D subshell, which is the 10 electrons. Right, and the 8 come from the 2 above it. So for a total of 18. And then the F, we said we have 7 orbitals for a total of 14 electrons.
So F itself only goes to 14, but it says 32.
Yes, yep.
So like if you did the total electrons, you do like 2 plus the 6 plus 10 plus 14. Okay.
Yes, yep. Any other questions? Alrighty. Okay, I think that's all I wanted to say there. Let me just check my notes. Okay, cool. What other questions do we have for me? Does this clear up quantum numbers? Yes, do we feel better about it? Okay.
We do practice problems like for the clicker questions.
Let me see. Yes, so this was one practice question you had. So, right, the whole thing that we're learning about here is atom anatomy. So in a hydrogen atom, right, we only have a single electron. So as you move away from the nucleus, those electrons just increase by the number that's in front of them. So the higher the energy level, the higher the energy. So for this question, which orbital has the highest energy in a hydrogen atom? Which one is going to be our answer? Which one has the highest N value?
6p.
6p does, right? 6p is the 6th energy level. That means it's the farthest away from the nucleus. So that's going to be its highest energy for a single electron atom, right? Whenever we have a hydrogen atom, we're saying this is just a single electron. Yep.
But I think like since there's only one electron, would get to like we only say the S orbital.
So we can always excite the electron by giving it energy, and it can reach the 6p orbital. It should, at the ground state, it'll only be in the s, but at an excited state, it would be the 6p. Questions here? Did that answer your question? Not really, probably.
I haven't.
Yeah, okay. Just know that the farther away for a single electron means it's higher energy. When we get into multi electrons, then it gets a little funkier. And that's where your question about like the 3D coming before or after the 4s comes into play. Yep. Yes. Yep. So it would just be happiness there. That's what would be in the ground state, right? It has 1s. If we wanted to draw the diagram for 6p, we have 3 orbitals in the p orbital, and then so it would just be the 1 there. Yep, and it would be the 6p. Okay, so here's a clicker question. Okay, so how many electrons can be found in the n is equal to 3 shell? Where'd you get 14 from?
7 times 2.
And where did 7 come from?
The 7. Negative. The 7 shapes of the orbital.
So, right, when n is equal to 3, you said 7, which corresponds to what orbital? Or what subshell?
F.
The F, right? So that meant that L is equal to what if it's F?
-3.
L, not F sub L.
Oh, 1, 2, 0, 1, 2.
Mm-hmm. So it can be 0, 1, or 2. Oops. Okay. So if L can equal 0, 1, or 2, M sub L can equal 0, -1, 0, 1, -2, -1, 0, 1, 2. How many total orbitals do we have? Nine. Right, we have 5 here, 3 here, 1 here. So how many total electrons can we have? 18. Does everyone see how we got to 18 from the question? Right, if I asked you, if I just ask you for how many electrons are in the 5F subshell, how does this change? What are our options now? Yep, right, so I'm telling you it's 5F, so what does that mean N is equal to? N is equal to 5. What is L if I'm telling you it's 5F?
Three.
It's 3, right? L has to be 3 if I'm telling you this is the F orbital. Right? 0 is always going to be S, 1 is always going to be P, 2 is always going to be D, 3 is always going to be S. So what's our options for M sub L? -3 to 3. Well, right, I'm asking you how many electrons, so we're like taking that into account because we know that there's always going to be 2 here, right? Okay, so we're just looking at how many orbitals. We're just looking at these 7, right? So how many total electrons do we have? Gonna be 14. Questions? Okay, so you just, yeah,
Does that mean, when you have multiple like S, P, D, F, that the shapes are overlapping each other?
I think so, yeah. Anything else? So I'm asking, so in this question, right, the one above it, we said how many electrons can be found in the N is equal to 3 shell. So we're just saying when N is equal to 3, how many electrons exist at that energy level? So we need to look at all of our options if N is equal to 3. And if N is equal to 3, then we're saying, okay, L can be 0, 1, or 2. It could be any and all of those. So if it's any one of those, how many electrons do I have per each of those options? And that's where 0, -1 to 1, -2 to 2 come into play. So we're saying everything under this bridge of N is equal to 3. How many electrons exist? In the second question, I'm asking how many electrons are in the 5F subshell. So I'm saying I want you to narrow in on the 5th energy level at the F orbital and tell me how many electrons exist here, right? So I've already told you what N, I already told you what L has to be. Now I have to ask, what can M sub L be? M sub L can be -3 to 3. I have 7 options there. Each of them can have 2 electrons, so I have 14 total electrons. Do you see the difference between those two? Okay. Yes, yep. I like umbrella and where do I have to get in my umbrella to narrow it down? Or like a cone, I guess, right? You start at the energy level is the big part and you have to funnel your way down. Great question. Anything else? Any other questions you have for me? Topics?
Is this what the questions would look like on quizzes or?
Yeah, you might have a couple of these for quizzes. You will do more electron configurations on probably Friday for Altimos. And that one is like the meat and potatoes of like quiz questions and stuff. Say your question again. Yep, that'll be a question. That'll probably have something of an energy and you have to get it back to a frequency or a wavelength. But that's usually 1 or 2 questions. But electron configurations is when you start getting stuff that is like and all this big stuff here. That one they test you on a lot. Yep. Yep.
Do you need to know how to draw the different ones?
No, nope. Just know that the p orbital is a dumbbell shape. Know that the s orbital is a sphere shape, and the d orbital has a clover shape. But you don't need to draw them at all. Just like know what they kind of look like. Yep. Mhm.
Do you just like 1 or 2 questions over like the whole other?
Yep. Yeah, absolutely. You probably will have one question on the de Broglie wavelength, which is not your typical wavelength. That equation will be given to you. But just know if you're asked for a wavelength and you're given a mass, that's always de Broglie wavelength. The other wavelength is C is equal to lambda. I don't know. I always draw frequency with the funky F because I don't like all the V's. So lambda times frequency. Then you also have energy is equal to Planck's constant times frequency. So you can combine these two and say energy is equal to hc over lambda. All of these are given to you, I believe. The energy is equal to hc over lambda might not be, but the speed of light and then the energy formula will both be given to you. And so we can say okay. So we can say if a photon has an energy of 7.14 times 10 to the negative 19 joules, what is the wavelength of the photon? How would you go about solving this question? Perfect, right? So the most straightforward way is to use the energy is equal to hc divided by lambda, right? You're given the energy, h and c are both constants, and then you're solving for lambda or the wavelength of the photon. So you can rearrange it and say that the wavelength is equal to hc divided by energy. Does anyone know Planck's constant? That's right, right? Okay. Dang, you do this long enough, it kind of sticks with you. And then does anyone know the units on Planck's constant? Joules times second. Right? If we look at the energy is equal to Planck's constant times the frequency, energy is always going to be in joules here. And then what are the units of frequency? Hertz, which is 1/seconds. So if we have a constant, those units need to help us get to our final answer. So joules times seconds, seconds being in the numerator would cancel out with the seconds from the frequency. So we're left with joules. What is the speed of light? You can use 2.998 or 3. I don't think it really matters. And then energy we're given as 7.14 times 10 to the negative 19 joules. Okay, and I end up with a wavelength of 278 nanometers, which is also 2.78 times 10 to the negative 7 meters.
Did you do percent per year? So you just
Yes, yep, so when you get it in your calculator, it'll be a small number, so, you get 2.78 times 10 to the negative 7. But just to put it in like a wavelength format, nanometers is usually pretty nice. You're usually gonna be given a wavelength in nanometers, which is times 10 to the negative 9th. And as a rule of thumb, usually your joules, your energy is gonna be somewhere around the magnitude of times 10 to the negative 19. Right, so here our joules is given times 10 to the negative 19. And then our wavelength comes out around negative 7 meters, or 3 numbers and then nanometers. So if you get around that ballpark, you're usually doing something correct. If you get something where your energy is like negative 11, I might go check your answer again. But that magnitude is pretty spot on for the questions you're going to be seeing. 278 nanometers. What's our range of the visible light spectrum? 400 to, it's going to be 800. Yep. What's the 400? That's shorter. So what color is that? Your purples and blues. What about the 800? That's going to be your reds. So where does our 278 fall? Out of the spectrum, and what's out of the spectrum? What comes right after the violet? Ultraviolet, right? Probably somewhere in the ultraviolet range. Right, less than our visible range. Out of our spectrum, we wouldn't be able to see this light. But might be able to give you a data.
Not about this. What were you saying at the beginning about there's a mass to like this kind of wavelength?
Yeah, the de Broglie wavelength.
What is that?
We talked about it very, very briefly on Tuesday. This one should be given to you, but mass wavelength is equal to that was close. H is equal to mass times velocity. So you have, this is your de Broglie wavelength. This is still ending up in meters. This is Planck's constant still. M is mass in kilograms. And then V is your velocity in meters per second. If you're given a mass in the question, then you probably want to use the de Broglie wavelength, and this is for like larger things, so you're probably not an electron. Yep. I feel like the most I've seen this question, I think I see it once a year or whatever. They're like, what is the de Broglie wavelength of this, right? That it usually tells you to find the de Broglie wavelength. Or this object, a baseball, has a de Broglie wavelength of this, right? So that should be your trigger word to use this equation. You just might need to manipulate a couple of things before you use it. Alrighty, any other questions? Yeah. So when we have a wave, right, that's a terrible wave. Right, it's going to cross the x-axis a couple of times. It'll have a positive amplitude and a negative amplitude. So from the time it starts the x-axis, crosses it, and then returns back to the x-axis, this is your wavelength. Yep, but between this guy and this guy, that's also a wavelength, and they're going to be the same. I did always just think it's easiest to find when it crosses the x-axis. So that would be a wavelength. You could also have a wavelength that looks like that, and that wavelength is going to be much shorter, right? Because it only takes this much time for your wavelength compared to the red one.
And that's related to period.
Yep, that's related to periodization or frequency due to the speed of light, right? Because within one wavelength, right, if we were to say that this was our gate that we're getting to, right? By the time it reaches the blue line to the purple line, that blue wave goes through 1.5 wavelengths. The green one's going through a lot more, right? So within that time frame, there's a higher frequency of the green wave than there is of the blue wave. And that's they're related to each other by the speed of light. Does that make sense visually? Okay.
So the motion that's described by the
Yes. Yep. Yep. It's just really zoomed in because we can't see that. Right. And if you think about like radio waves or microwaves, radio waves are really long. They have to go around buildings and cities, right? So those wavelengths are massive. X-rays or UV rays, right? They have to get through your skin, so those are very, very short. So they have a higher frequency. Anything else? Okay, cool. We'll wrap it up there for today. If you need anything in the meantime, let me know. And hope you have a great rest of your week. I'll see you next Wednesday. Enjoy your fall break if I don't see you beforehand.